This is problem 1, and in this one we're given a system with 3 masses. Let's start by drawing a diagram. So we've got mass 1 here, which is 3 kilograms, and it's at the origin. This is the x-axis, this is the y-axis. Then we've got a particle mass 2 with a mass of 4 kilograms, which is at 1 and then 2, so it's up here. So this is M2, which is 4 kilograms, and then we've got a third particle, mass 3, which is at 2I and 1J, so it's here, mass 3, and this is equal to 3 kilograms. And in the first part, we're asked to find the center of mass. Now, it's easiest to do this by considering the x coordinate of the center of mass and then the y coordinate of the center of mass. So because we've got these 3 particles, this is going to be m1x1 plus m2x2 plus m3x3 all over the total mass, which is m1 plus m2 plus m3. Now we're going to need to use this total mass quite a lot, so let's just calculate it over here. M1 plus M2 plus M3 is equal to 3 plus 4 plus 3, which is equal to 10 kilograms. So let's substitute our numbers into here. x1, that's 0, because the x-coordinate of this one is 0, it's at the origin. So we've got 3 times 0 plus m2, which is 4, times x2. This is at x equals 1, so that's times 1, plus m3, which is 3, times x3, which it's at x equals 2, so that's times 2. And then we've calculated the total mass as 10 kilograms. So this term here is 0, and so we've got 4 plus 6, so that's 10 over 10, which is equal to 1. So this is 1I, because it's the x direction, and then we repeat to calculate the y coordinate of the center of mass. So we've got m1y1 plus m2y2 plus m3y3 all over m1 plus m2 plus m3. So the y coordinate of this first one is 0, so that's 0 plus m2, which is 4, and the y coordinate is 2 because it's at 2j, and then this one's at 1j, so that's plus the mass of 3, which is 3 times 1, and the total mass hasn't changed, it's still 10. So we've got 8 plus 3, which is 11 over 10. So that's equal to 1.1, and that's J. So this tells us that our center of mass is at 1I plus 1.1 J. Okay, now part B asks us if the mass M3, so that's this mass here, were to get really big, would the center of mass shift towards its location, away from its location, or stay the same? Okay, so let's consider what happens. What happens when M3 is much, much bigger than M1 and M2? Okay, so we're just going to sketch over the top of this in red to show what happens. Now, if M3 is much bigger than M1 and M2, then this top line here is approximately equal to M3x3, as this part, the M1x1 plus M2x2, is negligible compared to this part. And on the bottom, because M3 is so much bigger than M1 and M2, we can ignore M1 and M2, and this is approximately M3. So these M3 on the top and bottom cancel out, and this is equal to X3. And the same thing happens for the y coordinate. Because M1 and M2 are so small compared to M3, we've got M3, Y3 on the top and just M3 on the bottom, which is equal to Y3. So this tells us that the center of mass shifts towards the location of M3, which is 2.0I plus 1.0J. Okay, so this is problem 2, and in this one we've got a rod here. Now the rod has a length of 1 meter, so this end is at x equals 0, and this end is at x equals 1.0 meters. And we're told that the linear density along the rod varies, and it's given by 1.0 plus 2.0x kilograms per meter. And what we're asked to find is the center of mass. Now we only need to find it in the x direction because this is just a one-dimensional problem. So for a continuous object, we know that the center of mass is equal to 1 over m times the integral of x dm. Okay, so what we're going to do is break our rod up into little bits. Let's consider this little bit here with a length dx, which is a distance x from this end of the rod. What we'll need to start by doing is working out, well, what's the mass of this little bit here? So dm is going to be equal to the linear density lambda times dx. And so what we can do is replace this dm here with this expression for dm here. So we can write this is equal to 1 over capital M, this is the total mass of the rod, times the integral of x times lambda dx. Okay, now before we solve this integral, let's look at this 1 on m. So what we need to work out is the total mass of the rod. To get the total mass of the rod, we're going to need to sum together each of these little increments. So we're going to need to do the integral of the amount of mass at each length along the rod. So this dm is given by this expression that we've just got here. So this is equal to lambda dx, and we're going from one end of the rod with x equals 0 to the other end with x is equal to 1. And so we can substitute in our expression for lambda here. We've got the integral of 1 plus 2x dx from 0 to 1. And now we can solve this integral here. So we've got 1.0x plus 2.0x squared on 2. And this is evaluated at 0 and 1. And so substituting in these limits, we've got 1.0 times 1.0 plus 2 over 2, that's just 1. So plus 1.0 times 1.0 squared. And then when we substitute in 0, it's 0. So we don't need to worry about that 0 there. So we've got 2. So we've got 1 plus 1, which is equal to 2. So this tells us that the total mass of the rod is 2 kilograms, which kind of makes sense when we think about it, because this end of the rod is 1 kilogram per meter, and substituting in here we can see this end of the rod is 3 kilograms per meter. So it suggests that on average it's about 2 kilograms per meter, and it's 1 meter long, so 2 kilograms makes sense. Okay, so now what we can do is work out this center of mass. So we've got 1 over m, which is 1 over 2. And then we're doing the integral of x times lambda. So x times lambda, that's 1.0x plus 2.0x squared dx. I just multiplied x by the lambda from here. And so this is equal to 1 over 2 times, now we're going to want to integrate this. We should put our limits on our integral. X is going from 0 up to 1. So when we integrate this, we've got 1.0x squared on 2 plus 2.0, and when we integrate x squared, we get x cubed on 3. And this is evaluated from 0 to 1. And so this is 1 over 2 times 1 times 1 squared, so that's still 1 over 2, plus 2 times 1 cubed, which is still 1 over 3, and then when we put in the 0, that's still 0. So we can go, well, this is 1 over 2 times, we can put a common denominator of 6 down the bottom, and then we've got 3 plus 4. So this is going to be equal to 7 over 12, or you could have just done this on the calculator. When we evaluate this on the calculator, we get 0.58 meters. So the center of mass is 0.58 meters from this end here. Okay, so this is problem 3, and this one really is quite challenging. So we've got a uniform soda can, so let's sketch it like this, and it's got a height capital H, and that height is equal to 12 centimeters, and the mass of the can is 0.140 kilograms, and initially it's filled to the top with soda, so the mass of the soda in the can is given by 0.354 kilograms, and then we drill a small hole in the top and the bottom, and the soda starts to drain out. And in the first part, we're asked, well, what's the center of mass of the can when it's full of soda? Okay, now the nice thing with this problem is that it's very symmetrical. So with our can, we can assume it's got the same mass up the top as down the bottom. And so the center of mass of the can is going to be equal to half the height of the can, so H over 2. And the center of mass of the soda will also be right in the middle, because initially it's filled all the way to the top, so we've got as much mass above the midpoint as below it. So the center of mass of the soda will be, well, the height of the soda divided by 2, but initially this will just be H over 2. And so the center of mass of everything is going to be equal to H over 2. So this is the center of mass of the can times the mass of the can plus the center of mass of the soda, which will be X over 2 times the mass of the soda over the total mass, which is the mass of the can plus the mass of the soda. And so since the initial height of the soda, X, is H, we can write this as H over 2 outside of the mass of the can plus the mass of the soda over the mass of the can plus the mass of the soda. We've got common factors on the top and the bottom, so it's just H over 2. And since we're told that the height of the can is 12 centimeters, this is just going to be 6 centimeters. Okay, part B then asks us what's the center of mass once it's lost all the soda. So in that case, we've got that the ms is equal to 0. So we can use this same equation here, but now we've got that the mass of the soda is 0. So when we do that, we have that the center of mass is equal to H over 2 times the mass of the can over the mass of the can plus the mass of the soda, which is 0. And so this will be equal to H over 2, and so it's still 6 centimeters. Okay, now in part C, we're asked what happens to the center of mass, which is H. So this is H, this is H, as the soda drains out. So let's refer to this variable mass of soda as ms dash. So ms is the initial total mass of soda, and ms dash is the amount of soda that's actually in the can. So ms dash is going to be equal to the density of the soda times the volume. And we can work out the density because we're told the initial mass. So the density is equal to the mass divided by the initial volume, and so this will be equal to ms, which we've got a number for. I'm just not going to substitute it in right now, times the initial volume, and that's equal to the height times the cross-sectional area of the can. So now we've got an expression for the density here, and this volume's actually changing. So we've got ms over h a, and the volume in the can is, well, it's got a height x of soda and it's got cross-sectional area a. So these cross-sectional areas cancel out, and we've got the mass of soda, which is actually in the can, is the initial mass of soda times the height of the soda over the total height of the can. Okay, so our expression for the center of mass is equal to h over 2 times the mass of the can plus x over 2 times the mass of the soda, which is the initial mass of the soda times x on h, over the mass of the can plus the mass of soda in the can, which is given by ms x on h. Okay, so let's times the top and the bottom by 2. We'll actually times it by 2h, because that'll make it a little bit prettier. So we end up with h squared times the mass of the can plus x times the mass of the soda, that's x squared times the mass of the soda, over 2h times the mass of the can plus 2msx. So this expression tells us what happens to the center of mass. You can see that as x drops from h squared to 0, then the numerator decreases, but the denominator also decreases. So it's probably easier to think about it physically. As the soda drains out of the can, the center of mass of the soda goes down, while the center of the mass of the can stays in the same place. So this is going to get the center of mass of the can and soda to drop. But then as this center of mass for the soda is going down, it's becoming relatively less important as the mass of the soda is going to 0. So eventually this mass of the soda is 0 and this term doesn't contribute at all. So it's dropping, but it's contributing less and less, which allows it to start coming back up to the center of the can. So when there's no soda left in the can, then the center of mass is back up here. So what happens is the center of mass drops and then comes back up. Okay, now part D is a bit of a challenge. What we'll need to do is look at this expression here, which we've just derived, and what we'll need to do is find out when is this a minimum. So in order to do that, you'll need to work out what dH dx is. So to work that out, you're going to need to use the quotient rule, which tells us that if we call h f of x, then this thing here we can call g of x, this thing here is h of x, then f dash of x is equal to g dash x h x minus g x h dash of x over h x squared. So we can work out what g dash of x is. That's the derivative of this thing with respect to x. So this term has no x dependence, this does. So this is 2x times the mass of the soda, and h dash of x, that's the derivative of this term here with respect to x, so that's equal to 2ms. So what we can do is substitute all these terms into this here to get f dash x, which is this thing. So this is f dash of x. So when we do that and simplify, we end up with 2h times the mass of the can times the mass of the soda x plus mass of the soda squared x squared minus h squared mass of the can, mass of the soda, all over 2h mass of the can plus mass of the soda x squared. And so to find the minimum, this f dash x has to be equal to 0. So we set this equal to 0, which means that just this bit up the top needs to be equal to 0. So we can solve for when this equals to 0. Once again, there's a fair amount of algebra. So we've actually got a quadratic equation here where this is x squared and then an x term and then a no x term. So with our quadratic equation, this thing here is our a, the thing in front of the x squared. This thing here is our b. And then this is our c, and our quadratic equation tells us that x is equal to minus b plus or minus the square root of b squared minus 4ac over 2a. So we can substitute these terms in here and then simplify it, and we end up with x is equal to the mass of the can times the height of the can over the mass of the soda, times minus 1 plus the square root of 1 minus mass of the soda over the mass of the can. And we can take the positive square root as x is the height of the soda above the bottom of the can, and that can't be below the bottom of the can, so it must be a positive number. So take positive square root. So now we have x, and then once we have x, the question actually asks us to find the center of mass, so h. So what we need to do then is substitute our expression for x, which we have calculated here, back into this expression here for h. And when we do that and simplify, we end up with h is equal to h times the mass of the can over the mass of the soda times the square root of 1 plus the mass of the soda over the mass of the can minus 1. And then we've got numbers for all these things, so we can substitute in. So we've got 12 centimeters is the height of the can. The mass of the can is 0.14. The mass of the soda initially was 0.354, and then times the square root of 1 plus 0.354 over 0.14, and then we've got our minus 1. Sorry, left off the brackets around that. And then putting all that into the calculator, we end up with 4.2 centimeters. So if you got that one, congratulations. That was really very challenging with quite a few mathematical steps, but hopefully the physical reasoning about what happens makes sense. Okay, this is problem 4. Let's start by drawing a sketch. So here we've got an olive at the origin with a mass of 0.50 kilograms, which is a mass much heavier than any olive I've ever heard of before. And then we've got in the xy plane a Brazil nut, which is at x equals 1 and y equals 2 here, and the mass of the nut is equal to 1.5 kilograms, which again is much heavier than any Brazil nut I've ever heard of. And we have forces acting upon these. So on this olive, we have a force which is equal to 2.0 I plus 3.0 J newtons. And on the Brazil nut, we've got a force equal to minus 3.0 I minus 2.0 J. And we're told that these forces act from 0 seconds, from t equals 0 seconds to 4 seconds, and we can assume that they start from rest. Now it asks us what is the displacement of the center of mass. So the easiest way to approach this is to actually use Newton's second law on the center of mass. So Newton's second law tells us that the sum of the forces is going to be equal to the total mass times the acceleration of the center of mass. So we can use this to calculate the acceleration of the center of mass, which is equal to 1 over the total mass times the sum of the forces. So the total mass is equal to the 0.50 kilogram olive plus the 1.5 kilograms of the Brazil nut. So this is equal to 2 kilograms. And then the sum of the forces, we've got these two forces acting. So we've got the force of the olive plus the force of the nut. And they're already in unit vector notation, which makes them nice and easy to add. So we've got 2.0i minus 3.0i, so that's minus 1.0i, plus we've got 3.0j minus 2.0j, so 1.0j. So the acceleration of the center of mass is equal to minus 0.50i plus 0.50j. Okay, so now I've got the acceleration, the constant forces, so it's a constant acceleration. So now we can use our kinematic equations to work out the displacement of the center of mass given the acceleration. So we can use our kinematic equation S is equal to ut plus a half at squared. In this case, we're assuming that they start from rest. So this term here is 0. And so our displacement is just equal to a half times the acceleration, which is minus 0.50i plus 0.50j times the t squared. And t is 4 seconds, so this is 16. So we've got 8 times minus 0.50i plus 0.50j, and so this is equal to minus 4.0i plus 4.0j. And so we've managed to work out the displacement of the center of mass without even having to calculate where the center of mass was initially or where it ends up. So this tells us how much the center of mass changes, which is what we were asked for. Okay, so this is problem 5, and this is also a little bit challenging. Here we've got a boat, and then over here's the shore. And here's water. And we'll let xb be the distance of the boat from the shore. So xb is distance of center of boat from shore. And just so that we've got it written down, the mass of the boat is equal to 18 kilograms. And then on the boat we've got a dog, and the mass of the dog is equal to 4.5 kilograms. And we'll draw the center of the dog there, and we'll let xd is the distance of the center of mass of the dog from the shore. So xd initial is equal to the d in the question, which is equal to 6.1 meters. And now the dog walks towards the shore this way along the boat. So x of dog, the change in x of dog relative to the boat is equal to 2.4 meters. So as the dog walks this way, the center of mass of the boat itself can't change. So the boat must move back this way a little bit. So that's what we're going to be working with in a minute. But let's just be very clear on what we've got here. So the change in the distance of the dog relative to the boat is 2.4, which means that the change in x of the dog minus the change in x of the boat is equal to 2.4. But as we've just shown in our little sketch up here, these are in opposite directions. So we can write that this is the change in displacement of the dog plus the change in displacement of the boat. The absolute value is equal to 2.4. So we've got one equation that we're going to have to use here to describe the relative displacements. Now the other equation will come from considering this center of mass. So the center of mass of the dog boat system does not change because there are no external forces acting. Okay, so we can say that the change in the center of mass is equal to 0, and the change in the center of mass is equal to the change in the center of mass of the dog times the mass of the dog plus the change in the center of mass of the boat times the mass of the boat over the mass of the dog plus the mass of the boat. So looking at this equation, we can multiply both sides by the mass of the dog plus the mass of the boat. And this tells us that the change in the center of mass of the dog times the mass of the dog plus the change in center of mass of the boat times the mass of the boat is equal to 0. And so rearranging this, we can say, well, the change in displacement of the center of mass of the boat is going to be equal to the change in displacement of the dog, center of mass of the dog, times the mass of the dog over the mass of the boat. Now up here we've got an equation with absolute values. So let's take the absolute value here and we'll make this into a plus when we take the absolute value. So now what we're going to do is substitute this term here in up here. So when we do that, we've got that the change in displacement of the center of mass of the dog plus the mass of the dog over the mass of the boat times the change in displacement of the center of mass of the dog is equal to 2.4. And so taking the change in displacement of the dog out as a common factor, I've got 1 plus the mass of the dog, and it's a 2.5 kilogram dog, divided by the mass of the boat, and it's an 18 kilogram boat, is equal to 2.4, which tells me that the change in displacement of the dog is equal to 2.4 over 1 plus 4.5 over 18. And solving that, I get 1.92 meters. So I've drawn my little sketch, and I know that the dog ends up 1.92 meters closer to the shore now. So it asked me to find out how far from the shore the dog was eventually. So this is going to be equal to the 6.1 minus the 1.9. And when I solve that, I end up with 4.2 meters. So the dog is eventually 4.2 meters from the shore. So even though the dog's walked 2.4 meters along the boat, that's caused the boat to move backwards, so the dog doesn't end up 2.4 meters closer to the shore. Okay, this is problem 6, and in this one we've got a softball which is traveling towards a bat. So it's traveling down like this at an angle of 35 degrees below the horizontal and with a speed of 15 meters per second. And then it's hit back by the bat. And in the first part, the final speed is actually downwards. So VF is equal to 20 meters per second. So we'll be using unit vector notation to answer this question because that's the easiest way. So let's let this be the I direction and this be the J direction. What we'll want to do at the start is split our initial velocity into an I and a J component. So to get the I component, this will be 15 cos 35 degrees, and solving that, we get 12.29 meters per second, and the J component will be 15 sine 35, which is equal to 8.60 meters per second. So in part A, we're asked to calculate the change in momentum between this initial state and this final state. So the change in momentum is equal to the final momentum minus the initial momentum, which is equal to m times the final speed minus m times the initial, velocity, not speed, which is m times the final velocity minus the initial velocity. Now, we'll do this in unit vector notation. We know that m is equal to 0.30 kilograms, as we're told that in the question. So the final velocity here is equal to minus 20 J, and then we subtract off the initial velocity, which we've written in unit vector notation here. So this is 12.29 I minus, because it's down, 8.60 J. And so this will be m times. Now in the I direction, we've just got the minus 12.29 I. And then we've got minus 20J here and plus 8.6J here. So this is equal to minus 11.40J here. So we're asked to calculate the magnitude of this. So in order to work out the magnitude of this, we'll use Pythagoras' theorem. And we'll do the square root of 12.29 squared plus 11.40 squared. The negative signs when we square it disappear. And so this is equal to 16.76. And so the change in momentum is 0.30 times 16.76, which is equal to 5.03, which is 5.0 kilogram meters per second, to two significant figures. Now in part B, it's pretty much the same question, except that now the final velocity is different. Rather than being down, the final velocity is now back towards the pit chart this way, and this is equal to 20 meters per second. Okay, so we do the same thing. We've got our change in momentum is equal to the mass times the final speed, but the final speed is now minus 20I minus the initial speed. The initial speed hasn't changed. And so this is equal to m times, now we've got minus 20I minus 12.29I. So this is minus 32.29I. And then we've got minus minus, so plus 8.60J. So once again, we use Pythagoras' theorem on this part here to get the magnitude of the change in velocity. So it's equal to 32.29 squared plus 8.60 squared. So this is the square root of 1116, which is equal to 33.4. And so this, the change in momentum, is 0.30, the mass times 33.4. And solving that, we get 10 kilograms meters per second as the magnitude of the change in momentum. So this is problem 7. In this one, we've got Superman over here, and he's being hit by bullets. These bullets have an initial speed of 500 meters per second, and then they rebound off him with the same speed but in the opposite direction, 500 meters per second, and there's 100 bullets per minute, and the mass of the bullet is equal to 3 grams, which is 3 times 10 to the minus 3 kilograms. So what we're asked is, what's the average force on Superman? So we can calculate the change in momentum of the bullets hitting Superman in 1 minute. So the change in momentum is given by the mass times the final speed minus the mass times the initial speed. And so this is equal to our 3 times 10 to the minus 3 times 500 minus 500. So these are in opposite directions, so they add together. So this is equal to 300, and this is in 1 minute. Now the average force is equal to the change in momentum divided by the time. That's from our impulse equation. So this is equal to 300, and this is spread over 1 minute, so 60 seconds. So dividing 300 by 60 gives us 5 newtons is the average force. So the direction would be in the initial direction that the bullets were traveling. Okay, this is problem 8. In this one we have a man lying on ice. The mass of the man is equal to 91 kilograms. He pushes a stone. The mass of the stone is equal to 68 grams, and he pushes it away from himself with a speed of 4.0 meters per second. And we're asked, well, what speed does the man acquire due to this? Okay, so initially everything's at rest. So initially the momentum is equal to 0. So we can assume momentum is conserved because there's no external forces that we're considering in this case. It's the man pushing on the stone, which is an internal force for our man-stone system. And so we can say that the initial momentum, which was 0, is equal to the mass of the man times the speed of the man plus the mass of the stone times the speed of the stone. What we're trying to find is the speed of the man here. So the speed of the man is equal to minus the mass of the stone over the mass of the man times the speed of the stone. And these are just things that we can substitute in. So the mass of the stone is 68 grams. So that's 68 times 10 to the minus 3 kilograms. And the mass of the man is 91 kilograms. And then this is times 4 meters per second. So solving this, we get minus 3.0 times 10 to the minus 3 meters per second. Now, the negative indicates that the man is moving in the opposite direction to the stone. So we were only asked for the speed. So the speed is 3.0 times 10 to the minus 3 meters per second is the speed of the man. If we had to give a direction, we'd say in the opposite direction to the stone. Okay, so this is problem 9. Now on this problem, we've got a block which is sitting here and it explodes. We have a left part and a right part, and the left part goes this way and the right part goes that way, and they slide for a while and then they come to a bit with some friction where they come to a stop, and the coefficient of kinetic friction on the left is 0.40. We're told that the mass of the left piece is 2 kilograms and that it slides a distance of 0.15 meters along this rough part here. And on the right half, the coefficient of kinetic friction is equal to 0.50. And it slides for a distance of 0.25 meters along this part. Okay, so this one here has a few different concepts involved. So first of all, we can think about the energy involved. So just after this explosion, the left and the right half both have some kinetic energy, and that kinetic energy is lost as work done overcoming friction on this rough part. So we can use that to work out how much kinetic energy they had initially. So the kinetic energy is used up as work overcoming friction. So let's write that down as an equation. For the left half, we've got a half ml VL squared is equal to, so that's the kinetic energy, and now we've got the work overcoming friction. So that's equal to the force times the distance. So the force in this case is the frictional force, so that's given by mu L times the normal force, which is mlg, and then times the distance dl. And we've got the same thing for the right hand side. A half mr VR squared is equal to mu r mrg times dr. Okay, now here we've got an ml on both sides, so we can solve this to get VL squared is equal to 2 mu L g dl, and these are actually things that we have the values for, so we can calculate VL. It's the square root of 2 times mu L, which was 0.40, times g, which is 9.8, times dl, which is 0.15. And solving this, we end up with 1.0844 meters per second. But then remember, it's traveling to the left, so we should put a negative sign there to show that it's in the negative direction. And we can actually do the same thing for the right, because even though we don't have the mass for the right, the mass cancels out. So we end up with VR is equal to the square root of 2 times mu r, which is 0.50, times g, which is 9.8, times dr, which is 0.25. And so solving this one on the calculator, we end up with 1.565 meters per second. Okay, so now we have the speed of the blocks just after the explosion, because that's the speed they had just before hitting the rough part, which we assume is constant because we assume it's not losing energy as it slides over the frictionless part. So now what we need to do is consider during the collision. So assume momentum is conserved during the collision, which is reasonable as no external forces are acting. Well, no unbalanced external forces are acting. There's weight, but then there's also the normal reaction force. So any external forces are negligible compared to the internal forces during the explosion. So initially the momentum's 0 because the block's at rest, and then that's going to be equal to mlvl plus mrvr. And what we're trying to work out is the total mass of the block. So we know the mass of the left hand, so we need to work out the mass of the right hand. So this is the term that we're trying to find. So let's rearrange it to make mr the subject. So we've got mr is equal to minus mlvl over vr. And these are things that we can substitute in. So we've got minus ml, which we were given, it's 2 kilograms, times VL, which we've calculated here. So this is minus 1.0844, divided by VR, which is what we calculated up here, 1.565. And solving this, we end up with 1.38 kilograms, but then we're asked for the total mass of the block. So the total mass is equal to ml plus mr. So ml was 2, mr we've just calculated is 1.38. So this is equal to 3.4 kilograms. Okay, this is problem 10. In this one we've got a couple of cars. The mass of car A is equal to 1,100 kilograms. The mass of car B is equal to 1,400 kilograms. So initially car A is stationary, car B comes in with some initial speed UB, then they collide, and then afterwards car A is going this way with some final speed, and car B is going this way with some final speed, and they come to rest due to the friction on the road. So in part A, we're asked to calculate the speed of car A just after the collision. So the useful bits of information that we're told is the distance that car A travels over the road. So we're told that car A travels a distance of 8.2 meters. So we can consider energy and go, well, the kinetic energy after the collision is converted into work overcoming friction. So writing this as an equation, we've got a half ma va squared goes into the work against friction, which is mu k times mag. So this is the frictional force, and then work is F dot the displacement, so the displacement is dA. So we've been asked to calculate VA, so you can see the mass of the car cancels out, and we've got VA is equal to the square root of 2 mu k g dA, and so this is equal to the square root of 2 times 0.13. We're told mu k is equal to 0.13 in the question, so that's where that comes from, times 9.8 times 8.2. So solving this on the calculator, we get 4.57 meters per second, which is equal to 4.6 meters per second to two significant figures. Now for part B, we're asked to do the same thing for car B. So we end up with this same equation through the same arguments for car B. So it's the square root of 2 mu k g and then dB this time. And we're told that car B slides a distance of 6.1 meters. So this is equal to the square root of 2 times 0.13 times 9.8 times 6.1, which when we solve it on the calculator, we get 3.94 meters per second. So that's equal to 3.9 meters per second. Part C then asks us to assume that momentum is conserved during the collision and use this to work out the speed of car B just before the collision. So use conservation of momentum. So we can write, well, MA/UA, so mass of car A times the initial speed of car A plus MB/UB is equal to MA/VA plus MB/VB. But we know that initially car A is stationary, so UA is equal to 0. So this term here is 0. So we're trying to work out UB. So we've got UB is equal to MA times VA. So that's 1,100 times VA, which we calculated up here, 4.57, plus MB, 1,400 times 3.94. Over, now we need to divide by this mass B, which is the 1,400. So solving that, I end up with 7.53 meters per second. It's a point which is equal to 7.5 meters per second. So then in part D, we're asked to explain why the assumption that momentum is conserved could not be valid. Okay, so it could be invalid if external forces are not negligible. So, for example, if the collision took place on a slope, then the acceleration, the weight force wouldn't necessarily be negligible. There could be other things that happen to the cars as well, like bits falling off, which could make this not be true. Okay, so this is problem 11. In this one, we have an elastic collision between two blocks. So here we have block 1 with mass m1 and it's sliding along. It hits block 2 with a mass 3m1, which is initially at rest. And then afterwards, We don't know exactly how they're going, but we've got block 1 with mass m1 and speed v1 going in some direction, and block 2 with some final speed v2 going in some direction, which we don't know as well. And we're told that this is an elastic collision, and because it's elastic, we know that kinetic energy is conserved. And we're told that initially the speed of the center of mass is equal to 3 meters per second. Now in part A, it asks us after the collision, what is the speed of the center of mass? Okay, so this one's not too hard because we know that because there's no external forces, there's only the internal forces, momentum is conserved, and so the speed of the center of mass does not change. So the speed of the center of mass afterwards is the same, so it's 3 meters per second. Part B is now more challenging because now what it's asking us to do is find the final speed of block 2. So let's go through what we know and write down equations for it. So we know that momentum's conserved. So we've got m1 u1 plus m2 u2, but this one has no initial speed. So that next term 0 is equal to m1 v1 plus m2 v2, but we know that m2 is equal to 3m1. So we can write this as m1 u1 is equal to m1 v1 plus 3m1 v2. Now there's an m1 in every term, so we can just divide by m1 to get rid of that, and we end up with u1 is equal to v1 plus 3v2. And let's label this one as equation 1. So that was taking into account that momentum was conserved. But the other thing we're told is that kinetic energy is conserved because it's an elastic collision. So we can write that down. The initial kinetic energy is a half m1 u1 squared. And then this second block has no kinetic energy because it's at rest, and that's equal to a half m1 v1 squared plus a half. Now instead of writing m2, I'm just going straight write 3m1 here times v2 squared. Now a half is a common factor, so we'll cancel that out everywhere, and m1 we'll divide through by m1 to get rid of it. And so we've got u1 squared is equal to v1 squared plus 3v2 squared, and this is our second equation here. Now what I'm going to do is I'm going to replace u1 from here with this expression from here. So sub for u1 from 1 into 2. So when I do that, I've got v1 plus 3v2 squared. So let's just expand this squared now. I've got v1 squared plus 6v1 v2 plus 9v2 squared is equal to v1 squared. So this now is the second half of this equation, plus 3v2 squared. Okay, so I'm looking at this part now. And considering just the bits in the blue box, I can cancel that on either side. I'll cancel some of this with some of that. So let's write this as I've got 6v1 v2 is equal to 3 minus 9, so that's minus 6v2 squared. And I can divide by v2. So I end up with 6v1 is equal to minus 6v2, which tells me that v1 is equal to minus v2. Okay, now what I'm going to do is substitute this back up into my center of mass equation, which I kind of had up here. So I can say, well, the speed of the center of mass 3 is equal to m1 v1 plus m2, which is 3m1 v2, over the total mass, which is m1 plus 3m1. So this is equal to m1 times v1 plus 3v2 over 4m1. The m1s cancel out. And so I've got 4 times 3, which is 12, is equal to v1 plus 3v2 But from this equation here, I've got V1 is equal to minus V2. So I can say this is equal to V1 minus 3V1. And so this tells me that V1 is equal to 12 on minus 2, which is equal to minus 6 meters per second, and V2 is equal to 6 meters per second. Okay, problem 12. This one's about a rocket, so we're going to need to use our equation Vf minus Vi is equal to the relative velocity times log of the initial mass over the final mass. And in this question, we've got a space probe, so the initial mass of the space probe, it's 6,090 kilograms. It's heading towards Jupiter with an initial speed of 105 meters per second, and then it fires its rocket and ejects 80 kilograms of fuel. So the change in the mass is equal to minus 80 kilograms, which tells us that the final mass is equal to 6,090 minus 80, which is equal to 6,010 kilograms. Okay, and we're asked to find the final speed of the rocket. So the final speed is equal to the initial speed plus the relative speed of the exhaust over the log of the initial mass times the final mass. And we are told the relative speed in the question, it is equal to 253 meters per second. So it's not too hard to substitute into this one. We've got 105 plus 253 times the natural logarithm of 6,090 over the final mass, which was 6,010. And we just solve that on the calculator and we get 108 meters per second. So that's how we solve that one.